So let's segue into our next part, where we're going to talk about the stellar spectra. All right. And we're going to talk about the stellar spectra. You guys remember this, the O, B, A, F, G, K, M's. What do we mean by this? What is it? What information are we gaining from these spectra? So what we can do is define spectral classes, right? We can say stars are classified into spectral types. And basically what we're saying is look at the spectrum of a star, right? And say the absorption lines. Well, the lines of absorptions. Here's some absorption lines. Right? Those lines are very dependent on the temperature of a star. So we say, look at a star, see what kind of spectrum it's giving off. From that, pull out information about its temperature and define this sequence, this O, B, A, F, G, K, M. Mnemonic to remember it, O, B, A, fine, Gus, and kiss me. That's how you remember this this spectral sequence. And this is basically a shortcut. What we're going to do is start putting stars into this categories so that we can cheat. You don't have to say, well, what star is this? I say, well, it's an O-class star. And that gives me a rough idea of like what its temperature is going to be. What kind of material do I expect is in that star? So that's why we define this sequence here. So on top of the OBFGKMs, on top of that, there's also a number scale, right? So we break our stars categorically by these letters based on basically their temperature. We'll delve into more details in a bit. But we also slap in a number scale. So perspective. I could have a O9 star. O9 is the coolest of a O-class star. Next in line will be a B0. Remember, OB is next. So a B0 is the hottest of B-class stars. Then I increment up. B1, go down. So the temperature is slightly cooling. B2, cooler. B3, cooler. All the way down to B9, where B9 is the coolest of B-class stars. And then, next category, A0, the hottest of A-class stars. Right. So, put in perspective, our sun is a D2 type star. Right. Furthermore, when I keep saying like our sun is an average type star, it falls in the middle of basically all the scales we can throw at: temperature, size, luminosity output. Our sun is very much middle of the road, average. So some things we've learned, right? We could plot stars based on their spectral class or luminosity. You guys are going to see this plot again, so remember details like this. Right? We start to put stars onto this plot. And here are the things we start to notice. The hottest stars, when we talk about weak absorption, remember that spectral lines, right? We're talking about the spectrum. Right? Right. The hottest stars, they'll have a weak absorption in the hydrogen and helium. And these are going to be the type O's. Then you go into like the me and the bandwagon. There's our good old soul. Right? Our medium-sized stars, they're going to have strong absorption in hydrogen. That's going to be closer to like our type A's. And then keep going down, and you'll find your coolest stars. These are things that have absorptions in heavy elements. They're going to have sometimes molecules there. Right? So the type M stars are definitely the coolest, and they have the heavier materials in them. And you're going to notice a pattern of what kind of elements are present and the temperature of the stars. So remember way back, this was now a while ago, section 5, when we're talking about properties of light. How does light interact with matter? We said that if you have a spectral line, that's a fingerprint. Right? I look at a star, I see the spectral lines of it. This is telling me what elements are there. They're telling me what is the composition of the stars. And by doing that, we've noticed that all stars are mostly hydrogen and helium. Right? Look at this A1 star. You see this line here, right? Big line, big line, big line. This is what's called the hydrogen Balmer lines. First mathematically predicted all the way back in 1885. And the idea is that take a hydrogen atom, an excited hydrogen atom, and it will radiate these 4 lines predominantly. And so if you see these 4 lines, you know you have hydrogen. Well, look across the entire spectrum of stars. They all have these predominant Balmer lines. We see that all the stars are of a large composition of hydrogen. This line here is how we know that. These lines here are how we know that all the stars are predominantly composed of hydrogen. Because we see hydrogen in their spectrum. So, some more fun facts we see. In terms of our sun, we see that our sun is by mass about 75% hydrogen and about 23% helium. I'd have to specify by mass. If you say by number of atoms, the sun is like something like 90-something% hydrogen atoms. Yes, hopefully in some of your labs you got exposed to some of this. All right. So, emphasis here. We specify the spectrum of stars. We say, all right, look at the spectrum, put you in a spectral class, and shortcut. Because we've assigned you into your spectral class, we already have a rough idea of what your chemical composition is. What are you made of? This plot is basically the exact same information on the next slide, but plotted in a slightly different way. When I say like a B-class star, its predominant radiation is going to be something that corresponds to a helium, specifically neutral helium. Go to RG, you're going to see ionized metal, some neutral metals. Basically, we're looking at plots of what is the predominant source of radiation. What's the predominant spectrum glowing from that star? So this is essentially the same information on the previous slide, but plotted in a different way so we can focus on, like I claimed, that chemical composition. All right, sorry about that. So, just a little table to summarize all of this. Still choking my water, guys. I'm alive, I promise. All right. So here's our spectral classes again, and we can associate our sun, G2. Our sun's in the G range. Going along with like, think about the color. We say our sun is a yellowish color. It's in the range of 5,000 to 6,000 Kelvin. All right. So I'll go with the top now. Our O stars. Our O stars, they tend to be a bluish color, and they're going to be incredibly hot. We're talking greater than upwards of 30,000 Kelvin. As you go down, we can see how the color changes. We go from blue to a bit of a white to a yellowish orange, down to the coolest stars that are glowing in a red. The M-class stars are around 25,000, 2,500 Kelvin in temperature. All right. So we're seeing what are the predominant materials in the star, and this goes back to why do we bother with the spectral classes? No. My wife tried to bring me a glass of water. Thank you. So, I'll repeat this. We have our spectral class, right? If we identify the spectral class, we have a shortcut. We can say, what's the expected temperature? What do we expect is composed in that star? What's in there? Now, as you notice, we have some more material down here. We get these LTYs. I didn't talk about them before because these are relatively new, right? We have our sun here, and we start to go further down the scale to an M star that's red, down to these cooler, smaller objects. We started discovering these things about 30 years ago. We started finding objects that were cooler than the class M's. And it turns out that's going to be things like brown dwarfs or some very high mass planets. So these things are not as bright or not as hot as a lot of the stars. Brown dwarfs are often described as failed stars, or a little bit different than that. All right. But the point is that we've had to, in recent history, recent for astronomy standards, expand our spectral classes. So I'm seeing questions of what techniques did they use? Basically, we got more and more sensitive equipment. We started to get bigger telescopes, and we could see further out there. It goes back to the brightness scales. Let me pull that up. So think back to those brightness scales. Here's the limit of what the human eye can see. Here's the limit of what a 1 meter sized telescope. Look at Hubble and Keck. All right. So we're starting to get better and better resolution. We can see dimmer and dimmer objects. So what's basically happened in the last 30 years is just we've gotten bigger telescopes. We've gotten a better ability to resolve the big objects. And that's how we're able to find these cooler objects. We just have improved our technology enough to resolve the smaller and cooler things in the universe.